Okay. I request all of you to mute yourself because I have done here, so I have muted everyone. If you want to ask any questions, you can unmute yourself and talk. Not a problem. You can ask any questions in between, also not a problem. But the someone is I'm muting it and unmuting immediately. So don't do that, please. So I'm going to mute everyone from here. If you want to ask any questions, you can raise the hand, or you can uh, unmute yourself and ask the questions, please. Should not disturb others, please. Thank you. Yeah, these are the registers. Okay, how they look like. Basically, the color coding is going to be used for all these registers because we have to make it as a the small in size. Okay, so that this size of the circuit should be reduced. Okay, these registers can be classified as the linear and non-linear. In linear, the fixed and the variable, as just now we discussed a bit about it, and different types of variable registers and different types of fixed registers. As the name indicate, the fixed means the resistance value cannot be the varied, and to vary the resistance by varying a knob, particular knob, we can change its value also. And the right side here in the non-linear thermistor, LDR, the varistor register, all these are what we can call them as the sensors, because they're going to convert a physical parameter into a voltage or the current. So we try to take those voltages and give to the controllers for the processing. Depending on the conditions we put in the processor, it takes certain decisions and do some actions on the relays or the LED or something like this. Say for example, in a temperature control system, okay, say for example in a room, we have to maintain the temperature between 30 degrees centigrade and 35 degrees centigrade, or 25 to 35 you can say. So if the temperature goes below 25 degrees centigrade, so the say for example any cooling system, maybe fan or the AC or whatever it is, should be off. If it goes beyond 35 degrees centigrade, the AC should be on, so that we can maintain. For this, we use a thermistor as the temperature sensing device, and we convert that. All these sensors will give the information in analog form only, that is the continuous with respect to time. But this analog signal cannot be processed by a digital system like computer or the system. So we need to convert that analog signal into digital. We use the A to D converter, that is the analog to digital converters. So once we get the information in the digital manner, we can give it to the processor, and to check the condition whether it value is less than 25 degrees centigrade, sorry, more than 25 degrees centigrade, or less than 35 degrees centigrade. Depending on that, we have to give the instructions in the program, and it should check the value, predetermined values, and it should take an action to whether to switch on or off the AC or the fan. Those AC and fans should be connected to the controller through the relay system. And the controllers, directly we cannot connect the fans or the ACs directly to the processor, because the processors will work with the just 5 volts DC. But for the fans and all, it requires AC of 230 volts and all, which is very high voltage and which produces the high current. So to handle such high voltage and high current devices, we use the relay, that is electromagnetic switch, what we call it as. So relays are what? The electromagnetic switch. So whatever the small projects we do in our labs can be scaled up using the relay system. The relay system is nothing but there is a electromagnetic switch which can allow the high voltage and high current to go to the uh, devices. But these relay systems can be controlled by the controller, which is very small voltage, just 5 volts DC or 0 volts. So to switch off the AC or any device, the microcontroller should send 0 volts on a particular pin or the port, we can say. If it has to be on, just 5 volts DC volts, okay, and just 5 volts DC will drive the relay through a relay drive circuitry. We're going to see all those in detail. Just I'm giving just an overview, okay, how we can use the sensors and all. That's fine. Color coding, I think most of you know to color coding of the registers. If not known, just you can have an overview of this. These are the different colors we use. That is a black, brown, red, orange, yellow, green, blue, violet, uh, and gray, white, gold, and silver. Okay, and there are different digits are there for these uh, colors. It is for black, it is 0, 1, 2, 3, and up to. For white, it is 9. And this gold and silvers are going to be used to identify the tolerance of the resistance. Say, for example, to remember these color bands, we have one. You can utilize any of your techniques to remember these color names and all. But one popular the line is there: the BB Roy of Great Britain has a very good wife. So just to the remember, we can, like this, so many other sentences are there. So the first letters will start from the black, brown, red, and so on. So each digits are what 0, 1, 2, 3, and so on. The first band indicates the first digit of the value. The second band is what? The second digit of the value. Third band is the multiplier. Okay, and the last band is the tolerance. Say, for example, the first band is, in this case, the first band is what? The black. Uh, so it might be the brown. Usually, the first band won't be the black. Usually, it may be because the black is 0. It won't be like that. So we can consider as the brown. The brown. The second is the red or the orange, we can say. So we can take any bands. We have the digits here. The third band is the green. Let's consider in this case as the brown, orange, and green. The brown is what? 1. The orange is 3. And the green is the 5. It is nothing but the 1, 3 is what? 13. 13, I think this color what they have used is closer to red because they have mentioned here. Let's consider 2, no, it doesn't matter. It's a brown, red we can take. So 1, 2. The brown is what? 1, the red is 2. There is a first digit is 1, second digit is 2. The third is what? The green. Green is what? 10 to the power 5. That is, we should not multiply the first 2 digits. That is a 1, 2 as it is into 10 to the power 5. So it is nothing but the 1 or 2 into 10 to the power 5. So it is a very high value. So if the resistance is more than 1000, we try to express the value in kilo ohms, mega ohms, and so on. So kilo means 10 to the power 3, mega is 10 to the power 6. So here the 1, 2 into 10 to the power 5 is there. So we can make it as 10 to the power 6 by adjusting the decimal points. So I can write it as 1.2 into 10 to the power 6. Hope you're understanding what I'm saying now. It is 1, 2 into 10 to the power 5 is there. I can make it as 1.2 into 10 to the power 6. So just to express it as in the mega ohm. So we can call it as the value is what? 1.2 mega ohm. And the last band is what? The tolerance band. It is a silver. So it may be either this gold or silver or no color also. So usually it will be the gold or the silver. If it is a gold, the tolerance will be the 5%. If it is a silver, the tolerance will be the 10%. Tolerance in the sense, so I'll give another the example. I think you can guess now. For 100 ohm, I want to have a resistor of 100 ohm. So what might be the color code for that? So the 100 in the sense, the first digit should be what? The 1, that is the brown. The second digit should be 0 because 100 is there, 100. Okay, so first digit should be 0, and the second digit should be 0. There is a brown. The 0, the digit color corresponding to the 0 digit was black. So we can say the brown, black. We need one more 0, that is 10 to the power 1. So 10 to the power 1 is what? Again, it is the brown. So if the color code is the brown, black, brown, brown, black, brown, it is nothing but the 100 ohm. Okay, like this. Say for example, 220 ohm is a 2 is what? The red, red. One more 0 we need, that is 10 to the power 1 is required. So we can say red, red, brown. And 10 kilo ohm, for example, I want the resistance value is what? 10 kilo ohm. For 10 is what? 1. The second digit is what? 0. For 10 kilo ohm, we're going to consider now. The first should be digit should be 1. The second should be 0. Okay, that form 10. So kilo means what? 10 to the power 3 we need. So 10 power 3 is nothing but orange. So if it is the brown, the black into 10 to the power 3 is nothing but 10 kilo ohm. Okay. Now the tolerance is nothing but it is the range between which we can have the value of the resistance when we measure in the lab. Say for example, 100 ohm is the resistance value if the color code is the brown, black, and again brown. Okay, its color coded value is what? 100 ohm. But if I measure in the lab with multimeter or ohm meter,
Sir,
it will
sir,
not
I
show
have doubt, sir.
exactly the 100
Sir,
ohm.
I have doubt.
Yeah, please.
Sir, if the register color is brown, black, brown, gold, then what is the value of register?
Yeah, that's what I'm explaining now. What is the color coding for 100 ohm? Tell me.
Brown, black, brown.
Brown. Okay. First, you concentrate on the first three color bands. It is a
Yes.
brown, black, brown is
Black,
what?
brown.
100 ohm. Okay. The
Yes.
last digit is what? Silver. Silver is
Silver.
will not decide the value of the register depending on the color coding, but it gives what? The tolerance. So that's what I'm going to explain the last band now. What is the meaning of the tolerance? So if it is a brown, black, brown, it is 100 ohm. But if I measure its value with the multimeter in the lab, it will not be exactly 100 ohm. Okay, so it will be either slightly more than 100 ohm or slightly less than 100 ohm. Slightly more in the sense, can it show 200 ohm? No. Slightly less means, can it show as 10 ohm? No, highly impossible. So that the resistance value should vary little more or little less. So how much more, how much less, that is decided by this, the either gold or silver. If the last band is gold, only the 5% will vary. The 5% of 100 ohm, that is color coded value. 5% of the 100 is what? 5 only, right? So 5% of 100 is 5. So it may vary 5 ohm more or 5 ohm less. That is 5 less means what? 95. That is 100 minus what in general what we say 100 plus or minus 5%. Right? 100 plus or minus 5% if the last band is the gold. The last band is silver, the 100 plus or minus 10%. In this case, the silver is there. Okay. So in the example, what for easy calculation, I'm taking a 100 ohm because it is very easy to calculate the percentage. Okay. For 100 ohm, what is the color code? brown, black, brown. If the last band is the silver, what is the tolerance band? What is the tolerance? 10%. So 100 minus plus or minus 10. 100 minus 10 means what? 90 ohm. 100 plus 10 means what? 110 ohm. So according to color code, its value is 100 ohm. But if I measure its value in the lab, it may show any value between the 90 ohm to 110 ohm. It may show 105 or 106, 107, or it may show 98, 99, but not beyond that limit. Not less than 90 ohm, not more than 110. So accuracy is very important. So of course, if it is gold, there is 5% variation will be there. Okay, either above or below. If it is silver, 10% varies. If the last band is not there, sometimes only 3 bands will be there. So in those, the 20% is the tolerance. That is plus or minus 20%. Not say, for example, if the resistance value is 10 kilo ohm, okay, so it doesn't mean that the 10 kilo ohm plus or minus 5 ohm or 10 ohm. The 5 ohm, it is not 5 ohm, 10 ohm, it is 5% of the color coded value. So in case of the 10 kilo ohm, we have to find 5% of the 10 kilo ohm. Then we have to less it and add it to that. Within that particular range, it should show the value. Hope this concept is a bit clear for you people, I guess. I think the who already have studied the color coding, it will be easy. For others, just you can go. This is almost the same what we discussed. Now the main agenda of the entire workshop is the simulation and discussing some projects. Before that, before the projects, we try to go through some sensors and we try to interface to the Arduino microcontroller, and we try to discuss some projects also. So here we are going to introduce in this the entire session the Tinkercad as the simulation, the software or the simulation tool. There are the different versions are there or different simulation tools are there, but here we are going to discuss only the Tinkercad. This Tinkercad is open source, and you cannot. There is no need of it downloading this to the system directly. Just you connect the internet, go to the Google Chrome, and type, or any browser, type the Tinkercad. So you'll find the software and just log in through any of your Google ID or Gmail ID. Okay, and you can the sign up and you can start working. So this Tinkercad can be used to develop some 3D animations also. Can do that also, but here we are going to restrict our discussion only for the circuits. So in this, the Tinkercad, one of the simulation tool, we can simulate either the analog circuits, the digital circuits, and also the microcontroller concepts also. The analog circuits in the sense what the in which we are going to use only the like circuits, Ohm's law, Kirchhoff's laws, and diodes related like that. In case of the digital circuits like logic gates and all, okay, we can simulate. And in case of the Arduino microcontroller, before that we see what is a microcontroller and the some of the concepts of it, and about the Arduino microcontroller in detail, and its pins and all, and how to write a program and all those things. So that is the major part of this the webinar series. Okay, the analog circuits, say for example, Ohm's law, for example. Okay, to verify the Ohm's law, just we need only one battery, that is RPS we can say, or cell we can use it light, and one ammeter we need, and then one voltmeter, and the register. Okay, this is we can select any of the register. Most of you might have used this simulation, the software. This simulation, in the sense, without the real time real components, we can do some experiments. Okay, and this has got the uh, the major role in the industries, especially in the manufacturing the industry. Before the going to the manufacturing, I think the most of you know the IC technology. The IC is the integrated circuit. So that will, whenever we call a circuit, it is having all the components like resistors, capacitors, diodes, transistor, and all. So instead of using these discrete components, so we go for the ICs, that is the integrated. As the name indicates, the successive addition is what the integration. In a small space, we try to add the components. It is a actually not going to add, creating that process we call it as the fabrication, that is IC fabrication. So using the semiconductor technology, so on a single semiconductor wafer, so we try to create the lot of the components. So nowadays the technology is like lakhs of transistors can be the fabricated in a single IC. So that's how it is going to go in the wide manner. The different scale of integrations are there. There is a small scale integration, the medium scale integration, large scale integration, VLSI, very large scale integration, ultra large. So those gives what the number of components, how many that we can integrate in the particular IC and all. So VLSI is one of the major the section, as you know, in the engineering technology and all. Related to that, uh, there is the Moore's law. I think heard about it. The Moore, who predicted how the IC technology goes. He said roughly after every 2 years, after every, so I'm going to talk about the Moore's law. It is related to the IC technology, that is integrated circuit technology. After every year, the number of components that can be fabricated in a particular, or the transistor that can be fabricated in the IC is going to be doubled. A little bit the accurately, it is nothing but after every 18 months, so 2 years in about 24 months, but little accurately after every 18 months, the number of compounds is going to be doubled that can be fabricated in a particular IC. That's why the features are going to increase. I think we are going to see in the beginning the mobile just we are able to talk, that's it. But nowadays, so we can do a lot of things. So it is because of the number of the processors is going to increase in a particular the mobile system, like a dual core, quad core, octa core, and so on. We're talking about the how many processors are there in that. So if the number of processors are more, I think the options will be more. That is the work is going to be the shared, the entire different the processors are going to share the entire works. Okay, so the speed also is going to increase. That is how it is increasing. And we are going to see in the laptops also, we're going to see a lot of change from the old laptops and the present day laptops, only in terms of the technology. Fine. So this is the Ohm's law. On the right, there are two circuits are there. The left circuit is the actual the circuit used to for the Ohm's law, but the right one is what is the circuit which is designed in the simulator. That is a Tinkercad the simulator. Okay. Here the same one power supply can be utilized from the list of the components, and two multimeters are these two are the multimeters. One multimeter is used as the millimeter, other multimeter is going to be used as the voltmeter. Uh, so we can vary these knobs and we can change the voltage, and we can see the readings in the uh, another the 10 minutes are there. Today I'm not going to start with the Tinkercad simulation and all. So in the next class, that is tomorrow, I'm going to explain the Tinkercad. But now I'm going to explain the few more the circuits, which are the analog circuits itself. Okay. So as I was telling, by varying the voltage in the RPS, we can see the variations in the voltage in the millimeter as well as the voltmeter. So this will give the same values, the what Sorry, some signal issue was there, so it was off and on. Okay. So this gives simulation or the virtual, the experimentation gives the exact values how we do the experiment in the lab. Okay. To find the current, that is I is equal to V by R, what we use for the Ohm's law, it gives the same value. This is the another experiment. That is the diode characteristics. I think you know the semiconductor diode. It is the made of the semiconductor. It is a N type and P type semiconductor. So we can make this diode as the forward bias or reverse bias. The forward bias in the sense when P type is connected to the positive and the N type is connected to the negative. Okay, you can see this is the diode now. This is the diode. We know the technique of identifying which is the N type and P type, or the anode and cathode. So P type is also called as the anode, and N type is also called as the cathode. So this ring, silver color ring is there. That is the cathode. Okay, or the N type we can say. Or if the P type, this is the positive, or the P type, or the anode we can say, that is connected to the positive of the power supply, and this is the anode which is connected to the negative of the power supply. Okay, if P type is connected to positive and N type is connected to negative, so we call it as the forward bias. So when the diode is forward bias, we know the current flows through it. It acts like a short circuit. If you reverse it, so current will not flow. So it acts like the single way. So one way, what we can say. So especially this diode has got the wonderful application to convert AC into DC. That is the alternating current into the DC. So as the name indicates, the alternating current flows in both the directions, and also it varies the value also. It is the instantaneous value will be changing. But the DC, so it remains constant and it flows in a single direction. For all the appliances in our home, we use only DC, but not the AC. Of course, in the light and all, we use the AC. But say, for example, radio, television, refrigerator. So all these devices will use only DC. But we plug those to the AC directly 230 volts. But actually inside it, there will be the device, what we call it as the rectifier. So which converts the AC into DC. So in the rectifier, the main component is what? This diode. So there are different rectifiers are there: half rectifier, full rectifier, bridge rectifiers, and all. Okay. But here in this experiment, what I am going to connect is what? One power supply and one ammeter. Okay, and one resistor and one diode. This resistor and diode are in series. This resistor limits the current flowing through it. Okay, and this diode starts to conduct after the knee voltage, what we say. When it is forward biased, the diode start to conduct after the knee voltage. Knee voltage means it is the voltage after which it is the forward voltage. When it is forward bias, the voltage drop because the diode we call it as forward voltage. When the forward voltage is more than the knee voltage, it starts conducting. The knee voltage, the value of the knee voltage for the silicon diode is what? 0.7 volt. For germanium diode is what? 0.3 volts. So it means that, so we concentrate on only the voltage across the diode, but not the applied voltage. This applied voltage or the RPS voltage is going to divide some voltage across the resistor and some voltage across the diode. So this diode voltage will be very small. It may vary from 0.0 to 0.717 something like. Once it's crosses 0.7 for silicon diode, for a small change in the voltage across the diode, there will be large change in the current. So that we call it as what? The knee voltage. You're going to observe it. Okay. When it is reverse biased, so means if you reverse the polarity of this diode, the current doesn't flow. Even if you apply either 1, 2, 3, 4, 5 volts and all. Okay. So it acts like the single way. If you apply very high voltage across this diode, permanently breaks breaks down. Okay, so we cannot use it further. So we have to apply the voltage within the limits means for any component there will be the sheet by the manufacturer, what we call the data sheet. So we have to follow the instructions from the data sheet. Fine. I think it may stop in the few minutes now. Any questions regarding this, please, today? Any questions, please? In the next class, I'm going to explain some other components, and I'll introduce this Tinkercad software. You can practice in the Tinkercad software. Yes, today's sessions. Any doubts in this, please? Fine. If no doubts, you can will wind up today. I request, as I had texted it to you, all people, if possible, try to download the Arduino software from the net in the laptops. If the laptops are not there, no issues. Just you concentrate on the sessions and make a note if any doubts are there. Later you can practice this. So without laptop also, later once the this lockdown is relaxed in systems in the college or in office or wherever, so you can practice this. Okay. uh, so it is the very important. So as we know, in this COVID situation, it is the unable to the practice with the real time the hardwares, especially the Arduino microcontroller. But we have the virtual lab. You can practice in the software itself. Okay, you can use the Arduino board, and you can use the sensors also. You can use the actuators also. You can write the program, and you can simulate it. So without hardware, so you can learn so many concepts, and you can practice some projects also. It is possible. Once this COVID situation is relaxed, you can buy the components. And from our side also, we are going to arrange certain kits also, which includes Arduino microcontroller, sensors, actuators, and all. But we are waiting for this COVID situation to relax, because we should be a bit careful with respect to even the kids will come should come to us, but not the COVID along with those kids. And also we are going to wait for a few more the days and all. I request all of you to be at home. Don't move around. Okay. Take care of you. Take care of the family, and be safe. Thank you so much, Professor M.N. Basarai, sir.